another consequence of the energy, of the surface energy of the materials, is the grain boundary engineering. So what that means is that, for example, if you grow a specific material, let's say from molten phase, from liquid phase, what typically happens is that you have nucleation events. Within this liquid, the crystalline solid crystals will form, and eventually the material will solidify. So the question is, when you go from this process, when you go from liquid phase to the solid phase, what will be the arrangement of the grain boundaries or the grains? Can you predict the grain boundary architecture, the geometry, and is there anything that you can tell about this? And the answer is yes. And the grain boundary engineering and the geometry of the grain boundaries strongly depends on what kind of materials you have within the material and what is their relative surface energy. So if you're starting from a single phase, from, let's say, if you're looking at the solidification of copper, then you will be interested at the surface energy between different grains of the copper, right? So you have identical material, and you're looking at what is the architecture between 2 to 3 or 4 grains of copper itself. If you have a multi-phase material, you can think about what is the surface energy between different materials. So let's say copper and nickel and other different combinations. So we will try to understand how this geometry of the grain boundaries can be predicted, and how can you tell whether the material will form spherical types of precipitates within the material. If you have the same material, what is the preferential geometry of the grains, etc. So if you have 3 grains of identical material, your intuition will tell you that they will form grains that have equal shapes and that their edges are 120 degrees. So you just assume you have 3 grains of the same material. There is nothing that would tell you that one of these angles should be different than the second and the third angle, right? Equally, when you have 4 grains in the three-dimensional case, then the grain corners will form these particular angles. And we will try to understand this in more detail. So we will start from the simplest case, when you have 3 grains of the same material, and we will try to understand how these angles behave if you, for example, exchange one material with the other, if one grain is, let's say, of a different material or different phase. So we will start with the very first situation. We will try to understand, and we will try to calculate. We will show mathematically that this angle should be 120 degrees. So we are looking at 3 grains that have the same phase. So we will label this particular phase with phase alpha, and we are labeling it with alpha simply because we will later on introduce different phases, so we have to distinguish them. So what we are trying to understand is that if these 3 grains are forming some kind of an angle and architecture, what exactly is the angle between them? So this will be grain grain 1, and it is phase alpha. This will be grain 3, or this will be grain 2. It will be also phase alpha. This will be grain 3, also phase alpha. So what we will be doing is that we are trying to calculate what is this angle here, which we will label as 2 theta. And to understand that, we have to look at the balance of the surface energies. What that means is that you have grain 1 and grain 3, and in between 2 of them, there will be the surface energy, which we will label gamma 1, 3. This is simply the surface energy between grains 1 and grain 3. In this particular case, there are identical materials. So it will be the surface energy of 2 grains with the same composition. At the same time, there will be the surface energy between grains 1 and 2, which we will label as gamma 1, 2. And in the same direction, this will be gamma 1, 3. So for this system to be in equilibrium, the surface energies have to be also in equilibrium. So we will do a very, very simple math calculation to show what this angle 2 theta is by understanding the balance of the surface energy. So the balance of the forces in horizontal. You're right, yes. I apologize for that. In horizontal direction, So what that simply means is that whatever is acting on the left-hand side has to be in equilibrium to the forces that are acting on the right-hand side. So I will just write this in a very simple form. So because these phases are all alpha, so gamma 1, 3 will be equal to gamma 1, 2. It will be equal to gamma 2, 3. And we will label this as gamma alpha alpha, simply meaning that this is the surface energy between two grains that have identical phase. So I can then write this. So whatever is acting on the left-hand side is gamma 1, 3. So this is gamma alpha alpha has to be equal 2 times gamma alpha alpha cosine theta. So what I'm looking is that this is just a simple projection of gamma 1, 2 and gamma 2, 3 in the horizontal direction. So they're equal because these are equal compositions. So their projection in the x direction is gamma alpha alpha cosine theta. There are 2 of them, so this is 2 times gamma alpha alpha cosine theta. So from this you can calculate that the cosine theta is equal to 1/2. From that we can calculate that theta is equal to 60 degrees, or in this particular case how we labeled it is that 2 theta is equal to 120 degrees. And again, what that means is that, again, what our intuition told us is that if you have 3 identical grains, they will form the grain configuration where these angles are 120 degrees. So again, this is the intuition, and this is a very simple math that told you that this is indeed correct. So we will try to look into a more complicated situation when you have different phases. So if you have materials with completely different phases, how their grain configuration will look like. So we will look into a system where you have 2 phases, and we will label them with alpha and beta. And again, I will draw a very similar situation like in the previous case. So there are 3 grains. So this will be grain 1, this will be grain 2, this will be grain 3. I will label this as theta 1, this will be theta 2, and this will be theta 3. So these are simply the angles with the individual grains 1, 2, and 3 respectively. So if this is the boundary between grains 1 and 2, we will label this surface energy as gamma 1, 2. This will be gamma 1, 3. And again, as in the previous case, this will be gamma 2, 3. So in this particular case, we will look into the y direction. So we will look at the projection of gamma 1, 3 and gamma 2, 3 into the y direction. So I will label this part as x and y. And the balance in the vertical direction then simply means that the x has to be equal to y. And then I can simply write that gamma 1, 3 times cosine theta 1 minus 90 degrees. So this is this angle here, right? So this angle here is simply theta 1 minus 90 degrees. And the projection in the vertical direction is gamma 1, 3 times that angle. Has to be equal to gamma 2, 3 times cosine of theta 2 minus 90 degrees. So again, I'm looking at this particular angle, which is theta 2 minus 90 degrees, and the projection of gamma 2, 3 in the vertical direction is what I just wrote. So this is simply then gamma 1, 3. So this will be sinus theta 1 is equal gamma 2, 3 times cosine theta 2. So we can write this equation in a slightly simplified form, just rewriting it. So gamma 1, 3 over sinus theta 2 has to be equal to gamma 2, 3 sinus theta 1. Okay, so what we just derived is a very general equation that tells you if you have 2 materials in different phases, you can predict what kind of grain structure they will form if you know their relative surface energy, gamma 1, 3, gamma 2, 3, etc. And if you have 3 grains that are meeting together, then you can generalize this And you can simply then write that this is also equal to gamma 1, 2 over sinus theta 3. So this is a very general equation. Once you know what kind of phases you have, you know what is their relative surface energy, and you can predict what will be the grain structure between them. So we will use this in a couple of specific cases, and I will demonstrate if you know, for example, what the surface energies are, what is their relationship, you can predict, again, precisely whether, for example, the material will form a precipitate, what kind of grain it will form, etc. So the first example will be when you have two phases. So you have phase alpha and beta. And again, we are looking in the situation where you have grain 1, which is phase alpha. Grain 2 is phase alpha, and grain 3 is in the phase beta. So we are asking a question of what are these angles? So this will be, again, theta 3. So using we will use the same configuration as before. So gamma alpha alpha will be equal to 2 times gamma alpha beta times cosine beta. And we will look into the situation where gamma alpha alpha is significantly smaller than gamma alpha beta. What that means is that, again, the surface energy between two grains of the identical phase is much smaller than the surface energy between two phases of different, or two grains of different phases. Okay? So if you do have this particular situation, you can show that, for example, gamma alpha alpha then will be approximately equal to 0. From that, we can see that the cosine theta, which will be here, is equal to 0, and from that cosine theta is equal to pi. I'm sorry, the angle theta is equal to pi. So what is the consequence of this analysis is the fact that if you have two phases for which gamma alpha alpha is significantly smaller than gamma alpha beta, the configuration that will be formed is that you will form a spherical precipitate that is embedded within the phase alpha. So there are many cases where you do have precipitates that are very well defined, that have very spherical shapes. And if that's the case, what that simply means is that the surface energy between the two grains of the same phase alpha, which is the host material, is significantly lower than the surface energy between the precipitate itself and the host material. Okay? So another type of an example, which is very specific, is when, again, you have two phases, alpha and beta, where gamma alpha beta is equal to 1/2 of gamma alpha alpha. And again, if you do the math, you can see that gamma alpha alpha is equal to 2 times alpha alpha beta cosine theta, which is equal to 2 times 1/2 gamma alpha alpha cosine theta, simply because we are plugging this. So we know that the relationship between gamma alpha alpha and gamma alpha beta is 1/2. And again, from this particular situation, you can see that the cosine theta is equal to 1, and therefore the angle theta is equal to 0. And what this particular case describes is the wetting of the grains that looks like this. So you simply have a grain alpha, and in between you will have a phase beta. This particular situation is called wetting of the grains. So there are, again, many situations where this type of equation or this type of relationship is roughly satisfied. And what that means is that the phase beta of the material will completely wet the grains. So what that means is that you have different grains of alpha phase within the material. So this is your host material. You introduce the material beta, and it will phase segregate, or it will form, it will wet the grains of the phase alpha. And I will just show you an example of this particular situation. So this would be silicon nitride, which is an amorphous phase. So this is silicon nitride. So these are individual grains of Si3 and 4. So this is crystalline material, and everything that you see in between is the amorphous silicon nitride. So in this particular case, what we are seeing is that you have grains. Again, they will form different types of configurations and the angles between them, but in between you will have a phase beta. Okay, so we just looked into two different extreme cases. One is when one of the surface energy is very small, and the other is when they're roughly 1/2 of the other. Okay, and again, these are very, very common types of situations, and this complete wetting of the surfaces is, for example, very important for soldering applications. If you have amorphous phases within the crystalline matrix, the amorphous phases usually phase segregate at these grain boundaries and form these wetted surfaces of the grains.